Hello, this is Math Reasoning for April 7th. In this video, I want to talk through the starting axioms for real numbers. So these are things about real numbers we can take for granted and doesn't require any further proof. Let's get to it. Okay. All right, so we're going to talk about real number systems. Before we go a step further, this is what makes real numbers real numbers. There are three words attached to it, and we're gonna go through the axioms that makes each of these words true. So, what is a real number system? It is a complete ordered field. So we're gonna go through the field axioms first. What field means is that we can make sense of addition, subtraction, multiplication, and division. So these are some objects we could do some kind of arithmetic with. So that's what it means to be a field. And ordered means you have a sense of, if you have two distinct elements, one is greater than the other. So that notion of this number being bigger than the other is the word of ordered means. And one more word, real numbers are complete. This in some sense means that there are no holes of real numbers. So there's no gaps between numbers. This axiom is way more subtle. So we'll come back to it at the end of the quarter, but I'll let you know what it means now. And it's a little bit difficult to grasp why that's necessary at this stage. But let's first look at field axioms. Okay. So let me just kind of zoom out a little bit. Sorry, maybe we'll start with the addition axioms. Okay. All right. So we're gonna talk about what it means to be a field first. So you have a set of elements. Let's call that F. So this is true for any field, but you could think of real numbers for now. If you want to call something a field, you should have elements called either 0 or 1. And you should have two different types of operations, plus and multiplication. Okay, and the following property has to hold for any elements of the field whatsoever. So the first or the 0th axiom for the addition is that if you take two elements in the field and you add it together, you'll get another element in the field. So that's what's called closure under addition. So if you add two elements, you'll get something else in that set. And that's what it means to be additively closed. Okay. And the next axiom is that if you're adding a few things together, so let's say x plus y and then plus z, the order in which you add things doesn't really matter. So you could do x plus y first, and then whatever that turns out to be, you add the z afterwards, or you could decide to add y plus z first, and then whatever that turns out to be, add it to x next. So the order in which you do the addition doesn't matter. That's why most of the time we'll just drop the parentheses. That's a property called associativity. You can do it in any order you like. The next axiom is similar but a little different. You could add it one element first or the second element first. It doesn't really matter. It's called commutativity. So x plus y means exactly the same thing as y plus x. And so that's commutativity, additive commutativity. And then we talked about the element 0 and 1 that's in the field. This has a special meaning. So the element called 0, whatever it is, if you add it to any element, you get back itself. So addition by 0 doesn't do anything. This is what, so 0 is called additive identity. It does not mess with the other elements. So you have to have, your field has to have an element that behaves this way before you can call it a field. And the last axiom for addition is that for any element x, there exists what's called negative x, which is the additive inverse. So what I mean by additive inverse is that x plus the additive inverse of x will always give you the 0, the additive identity. So there's something you can add to get you back to 0. So that has to be true for it to be a field. So these are the 5 axioms for addition. There's a similar set of axioms for multiplication as well. Let's go through it. Okay. All right. So the first axiom for multiplication is similar. It's closure, right? So if you multiply 2 elements in the field, you'll get another element that's also in the field. So multiplication gets you another element. Multiplication should be associative. So you can put the parentheses and multiply in any order you like, and you should get the same number in the end. Multiplication is commutative. So x times y is the same thing as y times x. Element 1 is multiplicative identity. So remember, with addition, if you added 0, you get back itself. There's a similar element for multiplication, and that's what we're going to call 1. So if you multiply and get back itself, then that's multiplicative identity, and we denote those by using the numeral 1. And finally, very similar to the additive axiom, but you have to exclude the 0. So as long as you have any non-zero element, there's x to the minus 1, or just a multiplicative inverse of x, and such that if you multiply by it, you're going to get 1, the multiplicative identity. Okay. So there's 10 axioms so far, 5 for addition, 5 for multiplication, and they're very similar. And then there's one extra ingredient this make this field, these two operations interact the way we want, is what's called the distributive law. So this is how you can mix the operations. So if you have an x and you're multiplying it into y plus z, then that is the same as what you get if you distribute the x to each of those elements. So x times y plus y, x times z, and then you add it afterwards. Right? So this is something that we kind of take for granted ever since we learned it in algebra class, but it's we need to take it in as an axiom for fields. So there are 11 axioms so far, and if you have anything that satisfies those conditions, then it's called the field, right? So far, we talked about this bit, right? So we know why it's a field. The next thing I want to talk about is being ordered field. So to be an ordered field, we have to go a step beyond that. So for this, we need 3 more rules. Okay. All right. So there's multiple ways to go about this, but the way the book is presenting order axioms is to define what's called a positive set. That's exactly how you think what it means. So you have inside of the field, you have to identify what's called a positive subset P. I'm going to call it P, such that for any 2 elements in the field, the first rule is that closure under addition. So if you take 2 positive elements and then you add it together, then you get another positive element. So adding 2 positive things gets you a positive thing. That seems reasonable. The next rule, same thing with multiplication. So if you take 2 positive elements and you multiply it together, you get another positive element. So it is closed under multiplication as well, at least the subset P. And the third part is the kicker, right? So if you have an element in the field, that means one of 3 things. Either the element is 0, which means it's an additive identity, or it's in the positive set, or if it's not in the positive set, or it's 0, then its additive inverse has to be a positive. So there's only 3 choices. And you can kind of think of this situation as being a negative number, right? And so you either have a positive number, or you're 0, or the negative of it, or the additive inverse is positive. There are only 3 possibilities. So this is called the trichotomy. And you know, this notion of positive set is a little bit difficult to work with. So another equivalent definition that we're going to use way more frequently than this positive set is that use the idea that we denote x is less than y as the same thing as y minus x, or y plus the additive inverse of x is in the positive set. So if you just like define this less than symbol to mean that the difference is a positive, or the bigger thing minus the smaller thing is the positive set, then the third rule, the third axiom P3, will translate to if you have any pair x, y in the field, then either they're equal to each other, or one of them is less than the other, or it's greater than the other. So there are 3 possibilities, and these 3 are what you have. So this is easier rule to use than P3. So that's what we'll do. Okay. All right. So we had 3 more rules. So let's see. We had 11 rules to be a field, 3 extra rules to be ordered field. And now it's time to talk about what it means to be a complete ordered field. So it only requires 1 extra axiom. So we have, I guess, we have 15 rules in all to fully describe real numbers. And that's this axiom. So completeness axiom. So if you have an ordered field, we call it complete if every non-empty subset of F that has an upper bound in the field has least upper bound in F. So this is a little bit hard to unwind. So let me give you a concrete example why this is needed. So let's say we have a set S. So let's say X is a number such that X squared is less than 2. So I want you to imagine this set. So it might take a little bit to imagine what it means, but really, if I draw it out, it's from -2 to, sorry, squared. So about negative square root of 2 to positive square root of 2, any number between those two numbers. So interval from -√2 to √2. So this set is non-empty. Yeah, there's some elements in there. So for example, 0 is within S because 0 squared is less than 2, right? So it satisfies that condition on the right. So it's non-empty. Okay. It also has an upper bound, right? For example, upper bound means, let's say M is my upper bound, M equals to 2. So if you take any X in S and you square it, so I claim that this number X has to be less than 2 because what we could do is we could just kind of square both sides. But I know that X squared is less than 2. So I guess what I want to say is backwards, I guess. Because X squared is less than 2, X must be between -√2 and +√2, which is less than 2. Okay, so it has an upper bound, but the field has to contain what's called the least upper bound. So 2 is an upper bound, but there's a smaller upper bound, right? Sorry, I'm gonna have to, oh, do I have a little bit more room? Oh, I'm gonna have to erase some of this, sorry. If 2 is an upper bound of this set, but 1.9 is also an upper bound, also 1.8 is even smaller upper bound, and you can get closer and closer to square root of 2 without actually going under it, right? So what's called the least upper bound is a number X, or I'll just call it M. It's a number M such that it is an upper bound. or let's say the set S, but anything smaller than this is not an upper bound. Okay. So let's let that sink in. So this is like a really complicated way of saying that square root of 2 is something that exists in F. Um, this seems like a really complex way to say something like that. But this is the right axiom. If you have this property, then you can kind of fill in all the gaps you have in real numbers. It's really needed when we start talking about things like limits of sequences. And it is hard to appreciate like why axiom like this will allow us to talk about limits and why not having this will break mathematics. But we'll get there eventually. You don't have to worry too much about trying to figure out how to use this axioms for now. We won't be using it for a while. Okay, so now that we know what it means for it to be a real number, so there were three things, right? It had to be a field, and then it has to be ordered field, and then finally it had to be complete. So I think it's instructive to go back and examine how the other number system fits in this list. So natural numbers, integers, and rational numbers. How much of the axiom does it satisfy, and how much of it does it fail? So let's actually, I kind of want you to pause this video and see if you can work out exactly which of the axioms are satisfied and which are not. After trying to figure it out, let's go through and discuss them. Starting with field axioms. Okay, so addition is something addition and multiplication is defined for natural numbers, integers, and rational numbers as well. So those things are something that's we inherit from the bigger real numbers. But one thing that immediately fails the natural numbers is the existence of the additive identity. So natural numbers, at least in our definition, does not start with 0. It starts with 1. So 1 is the smallest natural number, and then 2, 3, 4, and so on. So it definitely fails here for natural numbers. There is no member 0 where you add it and you get back itself. But the other two sets, right? So integers have 0 in it, so that works. And rational numbers have 0 in it, so that works. They are closed under addition. They're associative, and they're commutative. So at least where it's defined, natural numbers, integers, and rational numbers, they all satisfy these three axioms. And the additive inverse. So this is, again, where natural number fails, but integers and rational numbers are still fine. So you could talk about negative numbers and additive inverse. Even if you took the definition where natural number includes 1 and a lot of computer scientists, a lot of computer scientists includes 0 in the natural number set. In that case, this axiom would be satisfied, but it will still fail the next one where it doesn't have negative numbers. Okay. Let's talk about the multiplication axioms. So all of these will pretty much hold for all 3 of the sets, except for the multiplicative inverse. So if you're talking about natural numbers and integers, multiplicative inverse does not exist, right? So if you're talking about the element 2, for example, 2 is not 0. So you want the multiplicative inverse of 2, which is 1/2 in this case. Nothing exists for rational numbers, but for natural numbers and integers, they do not exist. Right? So this is where 2 of those sets will fail. And distributive law, right? So this holds for all 3 sets. So just kind of reviewing over all of the axioms, natural numbers and integers will fail some of them. It satisfies most, but there's this couple that it does not satisfy. Rational numbers, though, it satisfies all of these guys, all 11 of these field axioms. So rational numbers is a field. In fact, it's also an ordered field. So if you have a field and you can talk about a positive set, then you have these, it's an ordered field, and rational number is an ordered field. You don't have to know this for this class, but if you happen to know what complex numbers are, complex numbers satisfy all of the field axioms, but it does not satisfy the order axioms. So you cannot talk about positive complex numbers to have this, all 3 of these rules satisfy. Okay. All right, so the only difference between rational numbers and real numbers is that rational numbers are not complete. So square root of 2 is not a rational number. So every time you find an upper bound of a set, it's possible that sometimes you could have a infinite like descending sequence of something that's slightly smaller, but still an upper bound for the set. And that would be the case for this particular set. So if you're looking at this set inside of rational numbers, then you cannot find what's called the least upper bound if you're only looking for rational numbers. You need to go to real numbers to actually find the least upper bound. Okay, so I hope that made sense. Let's try proving things. Okay, so here's a list of some things, propositions that we can prove as long as we accept those 15 rules in the ordered field axioms that we talked through this video. And these are things that has to be true if we accept those rules. So you don't have to accept any more axioms for granted to prove these things. I'm gonna prove some of these. Actually, I think I'm gonna go and prove all 7 of these, and then ask you to try how to prove the rest on your own. I could go through all the proofs of these propositions, but looking at a video of me doing this is nowhere near as helpful as trying to figure out some of these stuff on your own. So I encourage you to try to prove some of these things on your own. If you get stuck, try the class discussion board and also the class, the Discord server, and then see if you can prove some of these things. And if you can figure it out, and if you're kind of want a feedback on like, was this a good proof? Does this count? I think that's a good feedback to seek out. So please do that, and then post your solutions, and maybe I can come back to give you feedback, and maybe other students will jump in as well. Anyways, let's prove some of these things. If you wanna try these on your own before I show the solutions, please pause the video and try it out. Take advantage of the fact that these are videos and it's not a real time. You can pause it, you can rewind, and then see if you can figure out some of these on your own. And other ones, you could look at the solution and kind of learn from it. Okay, so let's do these. Okay, so let's prove part A. Okay, so I want to prove that x plus z equals y plus z implies x equals y. Okay, so this is where we start, and we want to show that this implies that x is equal to y. Well, we know negative z is a thing. So we have an additive inverse for z. What we're going to do is we're going to add that to both sides of the equation. So we have x plus z plus negative z and y plus z plus negative z. And when I write these addition signs, I'm being a little bit sloppy here because I know that everything is associative. But here I started with the element x plus z, and I'm adding negative z to it. So I should have a parentheses here. And then from here, I can change the order of the addition. And I'm using associativity of addition, choosing to add it in any order I like. And now I'm going to use the definition of additive inverse. If I add z to its additive inverse, I get 0. Same thing on the right-hand side. Okay, and then finally, I'm going to use the additive identity axiom. So if you take a 0 and you add it to anything, you get back itself. This is the additive identity. Okay, so we started with x plus z is equal to y plus z, and we ended up with x equals to y. So that's what part A was. X plus z equals to y plus z implies x equals to y. So that's the end of the proof there. Let's keep going on. The next statement is x times 0 is equal to 0, no matter what x is. Okay. All right, so let's start with x times 0, and I want to equate this with 0. So I think what I want to do is, there might be other ways to do this, but I'm gonna rewrite 0 as 0 plus 0, and I can do that because 0 is additive identity. And then I'm going to use the distributor property to distribute the x to both of these 0 there. So x times 0 plus x times 0. Okay. Now, what I'm going to do is I'm going to, on the left-hand side, I'm going to add 0 to it. So I'm just going to do it this way. Sorry, that's supposed to be a 0. And I'm allowed to add 0 to one side because it's a additive identity. Okay, now I'm going to use part A. If I have x plus z is equal to y plus z, then x and y are equal to each other. So here, this is my x, this is my y, and this is my z. So it's x plus y is equal to x plus z. If that's equal to each other, then I could eliminate z from both sides and then say x is equal to y, or 0 is equal to x times 0. So I'm just using part A of this proposition. So I already proved it, so I can use that fact. Okay. Maybe I'll prove part C. Okay. So I want to show that negative x times y is same thing as negative x times y. So this one is a little bit tricky. What it's being asked is that we want to talk about negative x times y. So this is an additive inverse of x times y is the same thing as looking at the additive inverse of x times y. That's what I want to show. So an equivalent way to show this is this. Okay, if I have x times y and I add in negative x times y, so that's this element, then this should be equal to 0. Why am I phrasing it that way? That's what it means to be the additive inverse of x times y. It's a thing that you add to x times y, which result in 0. So if I can show this, then we're good. So let's see if we can work out what this is equal to. So the first step is to use the distributor property. So I can factor out the y here. Okay. And then I use the fact that negative x is an additive inverse for x. So x plus negative x is equal to 0. Okay. Whoa. Okay. And then by part B, 0 times anything is equal to 0. Okay. So we showed that this this guy right here is an additive inverse to x times y. So I proved part C. This might take a couple watches to fully appreciate. Let's look at the next statement. So negative x is equal to negative 1 times x. So here again, I think the tricky part is to work out what it's being asked. So you might think, well, negative x is already negative 1 times x. What is there to show? But really, starting with what we know, right? This is a notation for additive inverse of x, right? This is a notation for additive inverse the number 1. So what we want to show is that x times the additive inverse of 1 always work out to be the additive inverse for x itself. So let's see if we can prove that. Okay, what we could do is use part C basically. So let's see. Okay. Let's start with negative 1 times x. Using part C, if I use this in this expression, I can pull out the negative sign from one of the factors and put it in front of the product of the rest. So this is equivalent to negative 1 times x. This is by part C. Okay. And then this is equal to negative x because 1 times x is same thing as x. This is multiplicative identity. I hope that made sense. Okay. So this is becoming a longer video than I like. So I think I'm going to skip the next two. I think the next two are fairly similar to what we've done already. So I will skip those. But I did want to say a couple words about how to prove the last one. So let me do that. Part G. Okay. So I wanted to show that if x times y is equal to 0, then either x equals to 0 or y is equal to 0. Okay, so here, if I want to prove this, I think I want to do it in cases. Okay, so if x is equal to 0, then we are done. So if x is equal to 0, then that's the conclusion. So what we want to know is what happens if x is not equal to 0. If x is not equal to 0, then one of the axioms says that it has a multiplicative inverse. Then there is a real number x inverse. So I take this and multiply both sides by x inverse. Yeah. And then I think this was part B. X inverse times 0, that has to be 0 because anything times 0 is equal to 0. So say by part B. Then for the left-hand side, I could use associativity. So you can multiply x and x inverse before multiplying by y. Okay. And x inverse times x is equal to 1 by multiplicative identity. And 1 times anything is equal to y. So we end up with y equals to 0. So if x is equal to 0, then we have that case. If x is not equal to 0, then we can conclude that y is the one that has to be 0. So if x times y equals to 0, one of these two things have to be true. So that's the end of that portion. Okay, so I just kind of ran out of room, so that's it for that proposition. But oops, there are more propositions you can kind of look at to see if you can prove. So I've written out the propositions 1.44 through 1.46 in the textbook. These are similar type of propositions where you have to now start using order axioms and then see if you can prove like very reasonable statements using only the axioms. So I hope you try it out. And I think I'm going to end my video here.